right. Yes, applause. Applause also for the people behind the curtain, right? That got everything moving so smoothly. So welcome to the most exciting part of the conference. It's the debate on intelligence. I think that our community and probably most of science has ignored this concept of intelligence because it seems so difficult to define or capture. And I think what we're going to do with this exquisite panel of people that really know about intelligence is today to try to make some progress in understanding how robotics has already contributed and can continue to contribute to understanding intelligence. We're going to get started. As you see, it's a big panel. I'm going to start asking everyone a particular question. And I would like to ask each of you, when you speak for the first time, to say what your discipline is and what your institution is. Behind us are the pictures with the names, so people can match, can do facial pattern matching with the names. But it would be good to get. Well, I don't know, but did you study robotics?
No.
See, that's what I mean. You studied computer science, mechanical engineering, business administration, or I don't know. All right, so let's just get started. I'm going to start with Yannis, because he's exactly opposing me. What, in your opinion, are the basic components of intelligence, and how have we as a community dealt with these so far?
Thank you. I'm Yannis Alimonos from University of Maryland, working in computer vision and robotics. The question of intelligence is very hard. However, most people would agree that intelligence amounts to the ability to perform a large variety of tasks in a large variety of environments. However, in order to zero in on the question, we have to look at intelligence as it has been evolving. And a very interesting framework for that is the one by the archaeologist Mitten, who suggests that intelligence is basically three things: specialized intelligences, generalized intelligences, and cognitive fluidity. Specialized intelligences are things like perception, depth from stereo, shape from texture, or audio localization, etc. They're usually encapsulated processes, and they have to do with navigation, manipulation, dealing with the physical world, and with social signals. Generalized intelligences have to do with reinforcement learning, Pavlovian conditioning, trial and error learning, and these kinds of processes. And then cognitive fluidity has to do with the ability of all these processes to connect with each other. So each one talks to everyone else. That is the process of integration. So now, how has robotics dealt with all this? Regarding specialized intelligences, I think we have been doing quite well. And in every meeting, you see some more of them. Regarding generalized intelligences, we have also been making steady progress. Regarding cognitive fluidity, which amounts to the integration of all these processes, we have doing pretty bad over the years. However, the near future offers several opportunities to deal with this problem.
Great, that's great, and it immediately it reminds me of Vincent's talk, who was basically offering a view of integrating planning, control, and perception via all kinds of deep learning components. Is that an answer to the component that Yannis was saying we're not doing well on? Could that be the missing component?
Yes, so I'm Vincent Vagnouk. I am working right now at Waymo, but my background is on all things AI. I worked on speech recognition, I worked on computer vision, and then robotics. My answer to this is maybe. And it sounds like a weak answer, but it's actually a pretty strong for me in the sense that I've hated every single generation of AI until this one. I think we may have today a foundation for intelligence that is much, much stronger and has a much higher chance of being durable than any of the previous generation of AI systems that we have. And the answer to the integration problem that the systems we have provide today is basically backpropagation, saying that if you have two systems together that you co-optimize and you can have gradients flow between them, then you can have a degree of integration and impedance matching between those systems. It's a very low-level definition of integration, but it's one that actually scales very well and has worked very well up until now, and I think could be a possible answer to this problem of integrating different components of intelligence.
Yeah, I think actually that sounds very plausible. In your talk, you were advertising sort of the combination of vision, language, and action. Wolfram, I think that you want to take this one step further, right? And you want to include, if I understand correctly, as many modalities as possible, I guess, to reveal more islands of structure in the world?
Yeah, I think that, so I'm Wolfram. I'm a professor at the newly founded University of Technology in Nuremberg, and I'm a computer scientist, and I work on AI and trying to build intelligent robots. And so what I believe is that we are actually not taking enough efforts right now as a robotics community. I love the work that they're doing in terms of like foundation models, but if you have a closer look at that, what they are doing, they are mostly talking, like generating text, basically, right? They're generating images. They can also generate text from images, right? But they cannot act in the real world. And the reason for this is, I mean, that basically, if you want to take this to extreme, is that there's modalities missing, right? So if you really think about that, what is embodiment, then that basically requires that we also have a sense of touch, that we are able to basically correlate like the sense of touch and our forces, our perceptions in the sense of vision, like maybe also language, maybe also temperature, whatever we have, in order to basically generate the next actions. So that's, from my perspective, like our opportunity as a society, right, to go into that direction and take all the modalities that we are that are there, right? We are the ones who are able to generate those, and in order to build truly intelligent machines that do not only talk, but that also act in the real world, right? We need to have all the modalities and just do it.
Great. So now we have a plan for robotics, right? We're gonna do everything that you three said, and then we're done. But we still have a problem then, right? And that's to make these systems safe so that they can be around us somehow. And I want to ask Daniela, who in her presentation mentioned safety, how you think we can actually inject ideas into these ideas to ensure that these robots are safe to be around and maybe even behave ethically, which would be nice.
Yeah, so I am very excited about bringing AI and robotics together into physical intelligence. But I think in order to do that, we cannot have AI tools that hallucinate, getting our physical machines to behave in strange ways. And so as we think about safety in physical machines, there are several dimensions in which we can address this question. So one dimension is to develop tools that really ensure that the action that the systems take is within some kind of safe region. And we can come up with solutions that combine machine learning techniques with control theoretic techniques. And through these ideas, we could create we could create brains for our robots that will be guaranteed to provide output in a safety region. In my lab, we're experimenting with a technique we call barrier net, which is essentially a layer you can add to any model. And through that layer, you introduce task constraints, and those constraints will ensure that the machine that at least what the machine learning model outputs is within the desired region. But we still don't understand how that decision has been reached. Right? It's a safe number, but we don't know how it was arrived at. And big issue that we have with machine learning based solutions for robots, because when we look at the huge machine learning engines that we cannot explain, that we have no idea how they decide what they decide, it's a real problem when we put them on a machine, right? And so in most cases they seem to do the right thing, but what if they don't? And they often don't. And so for that I advocate really rethinking how we formulate our machine learning brains so that they are white box solutions rather than black box solutions. And by reducing the size, for example, as one particular method, by reducing the size, we can create systems, we can create models with fewer neurons in them. And if we have a model with fewer neurons, you can then extract a decision tree. You can write an algorithm to extract a decision tree that will tell you how the system reaches decisions. And so I think this way we can ensure that we have safe actions and that we can explain those actions. Now, there is another level that we can put on top of that, which is how aligned is the behavior of the machine to societal norms and societal values. And this is an important question, especially when we introduce robots in important societal applications, which we can aspire to do in the near future. And so for that, there are a lot of interesting computational techniques that are being developed by AI researchers and computer science researchers across the world, some at MIT, some at other universities, where we can study alignment. We can really, in a statistical way, we can compare what the machine does with what a set of humans acting in an ethical way according to our ethics norms would do, and then we can make corrections if we see that there are misalignments. But with respect to alignment, I would say that we don't actually have a clear path forward. And with respect to safety and explainability, there are ideas, but there is a lot of room for new ideas and for the young generation to come in and bring in their own suggestions.
Yeah, thanks, Daniela. I think that you, James, might want to say something about that, right? That not only do we need new ideas, but there maybe are some old ideas. Well, old is in quotes, right? I mean, well, logic, I guess, is old, but planning, I guess, is not that old. That could contribute. Maybe we introduced all of these problems only because we switched to neural networks, and the traditional robotic technologies don't even have these issues.
Yeah, thank you. I think when I started working on automated driving, I used to tell my team, it's one thing if your phone software crashes or your web browser crashes. It's a completely different thing if your car crashes. So there's a level of morality and moral responsibility that we have to build systems that are safe because people could die or get injured. And this is true not just for cars, but obviously robots that have some mass that could actually harm someone. And so how do we do that? And if someone comes to me and says, or comes to you and says, hey, I have this flying car that I trained with a neural network and it flies. Why don't you take a ride? Like, will you do that? And then you ask the question, well, will it crash? And the person says, I don't know. And I say, well, if it does crash, can you figure out why it crashed? No. How will you fix it? More data. How much data? I don't know. Like, these are not acceptable answers. So for me, throwing out physics or throwing out our understanding of how the world moves, because we're embodying these AI in physical systems, is foolish. The best example I heard was you can have a tiny device that actually has a model of satellite orbits that is essentially your GPS receiver, right? And it's actually calculating analytically the motions of those satellites so that it can triangulate its position and give you a very accurate GPS result. You could replace that system with a neural net that you train just by recording lots of measurements of GPS data, but that would be foolish. Like, you have a very compact representation of the physics of satellites and triangulation and geometry that you can use. So for me, the way that we like to use I'm very proud that our Lexus Teammate was the first product at Toyota that had neural networks built into it. And people were saying, this will never happen because you can't safety certify these things. But if you use them the right way, you can. For example, you can compute candidate trajectories that were trained on human driving behavior that the system proposes, right? And then you can take those candidates and you can validate them. And you can check that they obey velocity and collision constraints. And then you can optimize them for smoothness so there's ride comfort. So there's lots of ways you can combine classical methods with statistical methods. And to me, that is really exciting. Yeah. And I hope that will actually be a framework for where we can make systems safe. And I at the end of my talk, I mentioned it, but I actually firmly believe that there's a lot of fear right now of training AI systems that will basically have unbounded behavior. And they'll somehow decide, like Skynet, to take over and then destroy us all. But for me, I feel like as a responsible engineer, why don't we just make sure that we design as a human and validate the highest level of decision-making and behaviors of a system. And that way we can actually move forward and have confidence that these things are safe. I want a Lyapunov function amount on my controller that guarantees proper outputs.
So, James, I very much like what you're saying. I sense a little bit some controversy possibly in your statements. And I was wondering if somebody wants to maybe respond to that. Daniela is already ready to go. Okay, let's rumble.
Yeah. So I guess I agree with James that physics is important, and that's why I really advocate for physics-based methodologies and technology for neural networks. But I think that it's important to consider that there are some things that can be modeled with math. And those things are also not perfect. If you have a Lyapunov function, you still need the parameters. And so if you hand engineer all those parameters, you end up with brittle systems who may crash and who may give you the wrong results. And you also have to consider every single type of environment. You need different parameters for if it's sunny, or if it's raining, or if it's snowing, or if it's a country road, or if it's a city road. And so all of that, if it's done manually, it results in brittle systems. So this is where the machine learning, the data-driven statistical systems are very valuable, because they can introduce additional robustness. So they introduce robustness by processes that naturally figure out what those parameters are.
I think I agree with you.
So the other thing that is important is to remember that there are processes which we can reason about in the XYZ plane and through pixels. Those are very low-level processes. By bringing in machine learning, by bringing in neural networks, we can kind of raise the level of reasoning and the range of capabilities and the way in which we can interact with devices, because what we get is abstractions that are not possible to capture at the XYZ and pixel level. And so So I agree that we need a combination, but there is room for both. And we are at a point in our field where it's not enough to just reason about pixels and XYZ coordinates.
So it seems like overall you actually agree, which is too bad, right? But we got Wolfram who disagrees.
Yeah, Wolfram wants to disagree, yeah. So, I mean, I understand what James is working on, and I think that, like, for the justification purposes, self-driving cars, it's completely right to go in that direction. But if you think about us as a community as being like fundamental researchers with this question, like how can we build truly intelligent machines, right? And like basically replicate whatsoever us or any other creature, right? So then what we actually want to do is we want to understand how we work or how we can build something like this. We do not need to copy us, right? Because it's anyhow difficult, but like building something intelligent. And here's my counter argument, right? So humankind knows the equations of physics, right, since a couple of 100 years. And like for the entire humankind, we were actually able to do amazing things, like throw spears at deers, right, and kill them, right, without knowing the equations for a parabola. We could just do it, right? Maybe we don't need models, we maybe don't need math in order to build an intelligent agent. That's my claim.
Manuela, you have built a lot of systems.
A lot of systems. So I think that I agree with James, I agree with Wolf, I agree with Daniela. But there is something that I do tell you as my experience. So these neural nets are amazing at handling these situations, these tremendous amount of like the spectrum of situations and learning parameters. But I tell you one thing, and this is just sharing with you. When we are training a neural net to read documents, I mean, there are, for example, at where I work now, 70,000 different types of invoices, suppose. And then we train these machines to eventually figure where the address is, where the amount is, everything. And we train, we label, eventually they do it. And then guess what happens? Comes a new invoice, thousands of invoices a day, and the machine, the neural net, is saying, the amount is here, the amount is here, the amount is here, every single time. So what we need is this other layer that watches what these neural nets are doing and figure out the rule that for this form XPTO, the address is on position in the form 3151, and done. And we never have to call the neural net again. So the neural net enables potentially the access to this kind of knowledge that it would have been very hard to enter by hand, but it's also ridiculous to be calling this neural net for eternity that says that the name is always at the position 3151 for eternity, without extracting and abstracting to say, wow, that's it, in this form it's there, and it becomes constant time to answer versus calling this thing. So what I'm trying to tell is like this. There are many principles, there are many rules that can be extracted by this layer that analyzes eventually what neural nets do. But we cannot look at the world that intelligence is a one-shot thing. Look at what these neural nets are doing thousands of times a day. They're always saying the same thing over and over, so learn it. And my second comment is about exactly what Daniela was saying. So you know what we are missing? It's not machine learning. We are full of machine learning. Machine learning is great. We are missing machine teaching. So if you really have, even tic-tac-toe, if you have examples of tic-tac-toe, the machine is going to learn to play it beautifully, and it beats you every single time. It's incapable of giving you the rules of tic-tac-toe, saying you win if you have all these things on a diagonal, on a row, on a column. People play each one, the interleave plays. You draw when there are no more squares available. Zero ability to teach what is tic-tac-toe, or any other game. Tic-tac-toe, it knows because it's on the web. But try to invent a different game. Connect 4 with, like, instead of being the same color, 1 color, 2 colors, whatever. In no way. It will learn to play, it's incapable of teaching. Anyone the rules of the game. So what we need in some sense is for having this ability to extract principles, to extract rules, to extract understanding from whatever these machines are going to tell us. I already told you, the address is there. I already told you, you win when you do all of these. And then somehow we need another layer to explain or to extract a different representation to be able, without that, nobody's intelligent. They will say you the triplets of the Pythagorean theorem, but they will never tell you a squared plus b squared equals c squared. Never. So we are lacking that type of knowledge that we have the ability as humans, as intelligent creatures, to be able to generate. E equals mc squared, you name it. So I'm telling you, intelligence is over there, is being able to jump from that, you know, how do you say, scaled up, repetitive, and understand, aha, oh, a squared plus b squared equals to c squared. Aha, where's the aha part?
It's really interesting, right? Because it seems like, again, falling into Moravec's paradox. We're talking about math, we're talking about games. There's 3 people here that haven't said anything yet. And I think all 3 of you come from a little bit of an embodied perspective, right? And the notion of embodiment was completely absent in our discussion so far. So let's I don't know who wants to go first, but I want to hear you, turn this discussion back into robotics.
Yeah, I mean that's exactly my thought when I,
I know that,
heard about these things. Robots are physical systems. Okay, so you have to take the body into consideration. Otherwise, you are lost. And all bodies are different. So I don't think you can pre-program somehow. These things. The essence to me is the possibility for the body itself to acquire information, and to produce knowledge and to produce data. So it's not only data from the outside in, but it's data from the in outside. In fact, there are examples in perception where people show that what you see is what you are expecting to see, is not what is there. So unless you put the body into the equation, I think it remains a very interesting exercise, but limited to, stating very clearly, playing with words, and we all know that, is easier said than done, So in that sense, the fact that you can solve a linguistic issue does not mean that the issue is solved. So I heard, something like, if you can describe an action, the problem is solved. Forget it. I mean, I don't think this is the case because all bodies are different, and that is, the reason why I stressed very much in my presentation the ability to anticipate the effects. Not because, I mean, what it is the difference between planning and anticipation. The fact that if you want to anticipate, you have to think to the overall system. The memory, the perception, how you store information, how you retrieve information, how you make associations between what you know. So it's your experience, the experience of the body that is behind, for me. I mean, to me, this essence of intelligence for robotics. Then, what is called now AI, deep learning, and so on. It's certainly, I think it is certainly part of the game. It's not that, it's one against the other, one or the other. I mean, it's part of the game. But as I was stressing this morning, to me, it's maybe more useful to learn the structure of the system, like during evolution, because there you don't really need to interact with the world. While when you go around, you have to build your own experience by yourself.
I completely agree. And before I let everybody respond, I would to ask the 2 of you if you would like to add. Yes, please, Yasuo.
I'm Yasuo Kuniyoshi from the University of Tokyo. Been doing AI robotics and particularly constructive study of cognitive development. And embodiment is the keyword. So to add something, embodiment, in my view, is a constraint that provides structure in, for example, incoming data or moreover, whole interaction of the agent with the world. So I think this is the key to solve many issues. Particularly, I kind of resonate much with what Daniela said about the morals and things like that, and also the edge cases issues. I think these two, edge cases issue and moral issues, should be addressed together, because moral issues or ethics, what's good or what's bad, or trying to follow what's written like Asimov's law. You always have to deal with new edge cases. It's in the real world. Everything is slightly different situations, and I believe that you cannot handle all these with the machine learning methods. So why embodiment is the key? Because embodiment provides a constraint that acts on any data, so even outside of the training data. So everything gets organized, and it doesn't. So with your real body, you cannot do whatever movement. You are able to do only particular kinds of movement. This is the type of structure that is imposed on this. Moreover, extending this to internal organs, metabolism, and things like that. These, if you remember Damasio's findings, it gives you, interacts with the brain, and then does kind of processing that provides you your own way of, this event, this situation is good for you or bad for you, and things like that. So, so altogether, these will provide you a solution to even, completely out of the training data set cases. So.
Yep, thank you very much. And Brian, I'm sure you have something to add.
I've been saving up all of my argument time, so here we go. Actually, I want to jump back to what Manuela said, because I think there was a really important idea that snuck in here right at the end, which is that when we think about intelligence, we recognize this based upon ourselves. We're an entirely self-centered species, and our knowledge of what intelligence is and our belief about intelligence focuses on our own capabilities. And that may be wrong, that may be right, but that is what we do. And so when we think about these really amazingly statistically significant and powerful training systems, in the end, it may not make any difference at all if they aren't able to teach that information and pass it on to us. This isn't a new idea, and in fact, we should recognize that and celebrate that. In medical school, if you go and you train to become a surgeon, they have a rule. It's called watch one, do one, teach one. And you are not considered to be an expert at a procedure until you've seen it done, you've done it yourself, and most importantly, you've taught it to someone else. Now, in the computational world, we can take this idea all the way back to our most basic definitions of intelligence. This is all about, when Turing looked at this and said, intelligence is not about your mathematical complexity or about your ability to dexterously manipulate things. It's about your ability to fool other people. It's about your ability to pretend and to take that idea and to put into someone else's brain the idea that you are able and capable of communicating with them. So I also come from the tradition. I was trained originally as a developmental psychologist. I came into AI and robotics, and I've never left. But I still believe that when we look at these questions and we think about what is it going to take for us to look at a robot and say, is this machine intelligent? I think in the end, we're going to have to be able to say, what can it teach us? And what are we able to do from that? I'll also bring this around to my own work, which is in human-robot interaction. I don't think we can ignore the people in any of this equation. This is really about us.
Yeah, please, if you...
Just a short comment. To me, you know, the intelligence in the example you made about procedure, you know, is finding a new procedure better than the previous one. This will never happen if you just do it by collecting data, unless it happens by chance, which doesn't count in this case.
I'm kind of curious, Vincent. Sorry to take you now as the representative of you know, this deep learning robotics field, but I'm interested to hear your reaction about the comments on embodiment and the degree to which you feel that they're reflected in the way people are currently thinking about these problems.
Yeah, I agree with you that the embodiment piece is not sufficiently reflected in a lot of the sort of ways that people have been thinking about applying AI to robotics at large. I would riff a little bit on the idea that learning is about being able to teach. There is something really interesting there. I don't know if you've been following kind of the latest developments in large models with you know, GPT-o1 and things like this. There is a flavor of that in those latest results, where a lot of the development in terms of performance of AI systems is about chain of thought reasoning. It's about doing more at inference time, about producing chains of thoughts that explain a deliberative process, that explains a way of thinking about the problem so that you improve the net output. And I think this general direction is going to be developed quite a bit in the next few years, because a lot of people are seeing that this kind of foundation of having a trained model that is able to, in a sense, think symbolically about problems really is the next frontier in terms of reasoning using large models. So I'm very hopeful that this is something that will translate into this kind of being able to explain yourself and teach other people what your thought process is from directly the same substrates that we've been using in those large models in general.
Giulio, do you accept that as a compromise, as a bridge between what you would consider embodiment and deep learning?
Well, I don't know. I mean, I don't know. I mean,
that's a fine answer.
To me, I mean, I'm a sort of a fundamentalist in embodiment. I really think that you have to have the real body there, you know, and that you cannot explain actions, you know. Try to, one example that I always make is, you know, try to tell someone else how to do a knot without showing how to do it. I mean, this is impossible. So there are things which involve the body so much that you know, even the ethics, even, you know, the value system, you know, are really dependent on the kind of body that you have. Yeah,
I'm with you. Yeah, I'm with you.
So can I just add to
yeah,
that?
absolutely.
I would just say that the body is so important for the experiential side and for the feedback side. In fact, feedback, learning from experience, is an essential component of intelligence. And so with embodied systems, the body is critical in that process. And one thing I would observe is that many of the AI models that are deployed today, the deep learning structures, the transformer-based structures, they do not have recurrences in them. And so as a result, it's difficult to see how they're going to get the this feedback. And so So that's actually the thing I wanted to underscore, that feedback is important. Transformers don't do feedback. Deep learning doesn't do feedback. The body can do feedback. And other models that have recurrences in them can do feedback.
Before you answer, 1 second, I just want to say the next thing I would like to do is to open up for some questions that you might have. So please think already of your questions and maybe come down so that it's easy to pass around the microphone. If you have questions, if not, then that's fine too. But
my answer was just going to be yes, absolutely. Feedback is really the piece that is missing from the equation, and I don't think anybody's got a good grasp on that.
So I just want to add here to something to Julia. I really think that there is this dilemma between theory and practice. Nobody really can do a knot by reading a description of how to do a knot. You still have to see the example of how to do a knot. It's really true that this embodiment, you need examples, you need all sorts of things. But no matter what, if we discuss robot intelligence, there has to be a need for some abstraction. And another aspect that I think we need to understand is like this. Until this ChatGPT or this OpenAI or this robot tells you, I don't know that, until it realizes what it does not know, happily, and we tell what to do when we instructed the thing next time knows. I mean, can you imagine if we would be able to interact with the robot at the instruction level such that we talk the language, we talk something, that the thing learns something by instruction that did not know before, and it announced that did not know. Because I think that the problem with robots is that we, humans, no matter how much we can fantasize that we know how to program them or that they can learn, they still will find situations that are not covered by what we either gave as examples as data or we gave as principles. It doesn't matter. What if they would identify those situations and tell us? It would be remarkable. And then eventually we kind of figure it out, we find out, maybe we don't even know how to solve it ourselves. We figure out and we tell them, oh, do this in this situation. And the thing does it next time. So if we don't aim at that level of, how do you say, don't know, teach, learn, tell me what you've done, and talk with someone else, maybe that other system. If we don't understand these as this complicated kind of like interaction to acquire knowledge, I think we still don't have them being intelligent in that way or another.
So thanks, Manuela. Are there questions from the audience? Do we have a microphone?
Thank you very much.
Yeah, okay. I mean, please go ahead and...
Thank you very much. It has been quite fun. My question is about the collective intelligence for robotics. So where do you see value to collective intelligence for robots, and in which part of the development of a robot it should be handled? Thanks.
Are you directing that question just as the whole panel? At the whole panel? Yeah. Okay. So question 1 is collective robotics.
Collective intelligence for robotics.
Collective intelligence.
And in which part of the development process of a robot should it be handled?
Okay. Yeah.
Yeah, great panel. My question, I was thinking a lot about driving, and when, at least in the US, we have to do like 50 hours, I think, before you get your license. But you have two things. You have like the dynamics from all of your life experience. You have heuristics, kind of like Manuel is talking about, like when you're in a skid, you should do something. And you also have the network that's kind of been evolved. So maybe all 3 or 4, however many, combined. I guess that's a question, maybe a kind of open-ended question for the panel.
Okay, second question. I don't know, I have trouble remembering questions, so...
And that was long.
Exactly, yeah. Okay, so let's... Raja, you have a question?
It's a comment. So I think, and it's a question, of course. First thing, I think what the body does, it simplifies our lives. So my question, if you wish, it's not about feedback. It's about the fact that because action simplifies the flow of information that we receive and which the brain tries to process. So a way to reduce this complexity, this continuous flow, is, of course, to go through a channel which is action. Action is very limited. So action makes the word have sense, meaning. And the meaning is through action, what we can do. I liked very much a citation of Italo Calvino about imagination. And imagination gives you this impression of the complexity of what is possible. Action is about what is possible in the real world. And this is why it's important to have a body. Second thing, it's important to have a body because this notion of semantics. So large language model, and I loved the example given by Manuela actually now. They don't understand what they are doing. Why? Because they don't understand anything. They don't have semantics. They don't have attachment to the real world.
Thank you.
Comments?
Let's just collect the last question, and then I know there's more, but let's work on these four first. The fourth one.
Yeah, so my question was more to intelligence by itself. If you think that intelligence is the ability to understand and apply knowledge, and on the other side, you see that the network is dealing with tokens, which are just referring to some information, how can you speak about intelligence if all the network is doing is where to find the answer and not knowing the answer itself?
Okay, so we have four questions. Let's process them in order. The first one was about collective intelligence. Who feels knowledgeable? Okay, 2 hands go up. We have 2 answers. Maybe Wolfram first. And
yeah, I can give my few cents on that. So if you think about like this entire cloud kind of thing that is happening right now, these foundation models, it's basically collective intelligence, right? So we are basically collecting all the data, and all the data is available to all the robots in the world. So, I mean, collective intelligence will emerge from us using this technology to basically build intelligent machines. So there's no difference between a single agent and multiple agents.
A plus for having a short answer.
I'll make it short. I remember when I was a faculty at Carnegie Mellon, one of my machine learning colleagues told me, I know this algorithm's going to work, but my robot breaks down before I have enough data. And instead of having one robot collect 10,000 hours of data, you have 100 robots collect 100 hours each, and you actually make it really robust. So being able to share training data, essentially parallelize the aggregation of experience, and I think it's actually artificial experience if you virtualize it. But the other thing I would say is, when I have 4 kids, and every kid that I have raised spilled milk at least 50 or 100 times until they learned how to grasp a cup. But if we can actually teach a robot how to manipulate and grasp a cup, we could just copy that memory and that skill into other embodiments of the robot. So there's a huge advantage for this collective intelligence.
Great.
Cloud robotics.
Yeah, wonderful. The second question, I think, was about autonomous driving. So who? Yeah, James, please.
I'll make it short. So you mentioned about 50 hours for a human driver to learn how to drive. Actually, there's a lot of evidence that people have been passengers in cars for tens of thousands of hours. Yeah. And whether you believe in mirror neurons or not, you're actually building a model of driving. You're building a model of traffic. You're watching other people drive. You're looking outside, and you're basically learning how to drive and predicting how other cars will behave just by being a passenger. So there's actually a lot more hours of training that you've done by the time you're old enough to get a license. But for me, I feel like we want to actually make autonomous cars that are better than people, because I'm not sure society will accept an automated driving system that's just as good as a human, because human makes lots of mistakes. And the fundamental problem is that people have empathy for humans that make mistakes. If somebody makes a mistake, I think to myself, that could have been me. And I feel sorry for them, and I can understand them. But if a machine makes a mistake, I'm ready to blame that person or the person who programmed it, right? And I think a lot of people do not have empathy for a machine that makes a mistake, and that's a barrier to these systems.
No, I just want to jump in, what's interesting is that machines and humans make different mistakes. And so it's better to think about putting it all together into a shared autonomy system where the human can watch the machine and the vehicle can watch the human. The robot car will never get distracted or fall asleep at the wheel. At the same time, the human will never confuse a white truck for a cloud. And so it's really important to think about how we deploy the robots. And because we don't have perfect systems, and I don't expect we will have perfect systems anytime in the near future, it's important to ask what should the people do and what should the robots do? And how can we create, this is going back to collective intelligence, how can we create systems of humans and machines, robots, working together that are better than humans alone, that are better than robots alone, that are more robust and more capable?
Then there was the third question from Raja.
Can I just make just a very, very short about what you said? An intelligent robot is a robot that could exploit being carried around in a car without driving it. That's, I think, is the essence.
Yeah, that actually is a funny story, right? In Germany, the required number of hours that people take to pass their driver's test is going up. And they have investigated this and found one of the reasons is that kids drive passively. They actually check their cell phones while they drive, so they're not having this passive driving experience, and they need more hours. Exactly. There was nothing else to do, right?
No, but it's important to think about driving, which is like this. No matter what, you can take the test as many times as you want, and you'll drive when you pass it. It's really interesting that
it's only in the U.S.
Everywhere, in Portugal too. You can take the test 3 times, and then you can take again 3 times later.
Not in Germany.
You can fail the test for life.
Yes.
For life.
Yes. If you fail 3 times, I don't know the exact number.
You can come back 1 year after.
But then there's a special, actually, like
you pay more.
Psychological evaluation if you're mentally fit to drive a car.
No, but also this drive, I think that is very important, but also it's something we should notice is like this. Driving, if you look at everybody that drives a car, every single person can drive a car, except for the
Germans.
the Germans. So it's an intelligent task for sure, which is available to all. So it's not a Nobel Prize winning task.
I want to add something to James said. People are not sympathetic to machine errors. I think the reason is that partially because machines make errors very differently from humans. So the way it deviates, the system deviates from the correct situation to wrong behavior is completely different in humans versus machines. So here, embodiment, I think, is the key because it doesn't specify each data, but it's always there. Embodiment is always there. It constrains everything. So I think that's a way to ensure that the machine starts to do outrageous, mistakes.
So unfortunately, we're running out of time. So I think we're going to basically label Raja's comment as a comment. And then we're going to still have the open duty to answer Darius's question, which was about basically whether a neural network can know something or not, and whether that's a difference. I don't know if somebody wants to.
I forget that question. Can you repeat the question?
The question is that the network actually knows just the reference to the information and does not know anything about the information. So it would be like knowing in which book is the answer without ever reading the book.
Well, so that's a problem, right? I mean, it's if you see a solution and you kind of copy it from someone and you don't understand how the solution was derived, it's a problem. It's back to what Raja was saying, that machine learning is a kind of a lexical process. It's next token prediction. There's no notion of semantics. If a machine learning system recognizes this as a glass, it does so because it's seen a lot of other images where the pixels had patterns similar to the patterns in this image. So I would say that we have a lot to work to bring semantics, to bring meaning into this world. So let's say I know that the pixels look like the pixels in other pictures that people say were glasses, but what is a glass? What do I do with it? What's the purpose of a glass? The machine has no idea that the glass is supposed to carry liquids and you're supposed to hold it like this, not like this. So I think that there is just a lot about the physical world and about the meaning in our lives that we need to figure out how to incorporate in our machine learning engines.
So I think, this was just a short, almost hour for us to discuss. But I think it's clear that we have a long ways to go in many respects when it comes to robotics as a whole, but also intelligence in the context of robotics.
I think we are closer. We are getting closer.
We're getting closer, but that's not a very strong statement. But I would like to thank the panelists very, very much. I mean, all of you are incredibly smart people with great experience in answering these questions. It was fantastic to see you all discuss together. I really appreciate that. Thank you very much. I would like to thank all of you for hanging in here so late and for the great questions. I apologize to those who won't get a chance to ask their questions. And, we will be back at some point, and we'll keep coming back until we have figured it out. So thanks a lot.